applications of Rademacher's theorem for Carnot groups is to the theory of embeddings. Indeed, we shall then show that there are spaces like the Heisenberg group that are doubling metric spaces or even Alfors regular metric spaces that do not admit any biLipschitz embedding into any Euclidean space. So let's see this application. I'll present this following theorem as an implication of Pansu's differentiability result for Lipschitz maps to the theory of embeddings, biLipschitz embeddings of metric spaces. So this is really a result that is based on Pansu's Pansu's version of Rademacher theorem, but it was observed by Sams, so around 1996. So this is the theorem. So suppose you have G non-abelian or non-commutative Carnot group. For example, I mean, what does this say? This said that G is a Carnot group different from RK with the sum. Suppose you have a subset of G that is a measurable subset of positive measure. So measurable and of positive measure, the back measure. And let's fix any n natural number. Then we claim that there exists no map from U into Rn, where Rn is equipped with the Euclidean distance, that is a biLipschitz embedding. Namely, what does it mean? This means that it's a map. So we are claiming that there exists no such a map, that for some constant it is Lipschitz, but also has a lower bound like Lipschitz. So the map does not necessarily have to be surjective. So it's an embedding necessarily. So this is true for all x and y in U. And these distances are on the target, we have the Euclidean distance, and in the source, we have the Carnot-Theodori distance associated to a Carnot group. So we claim that there exists no such a map for as soon as G is a Carnot group that is not abelian. Okay. As I said at the beginning, this is following from Pansu's differentiation theorem. So let's remember what is Pansu's theorem. And maybe since I'm going to restate it, I'm going to state a slightly stronger result due to Magnani. And it's the following. So suppose you have G and H Carnot groups. And then you have U, a subset of G measurable. And you have F from U to H, a Lipschitz map. Then the result says that for almost every point P in U, F is intrinsically differentiable at P. Okay. We proved this result when U was equal to G, okay, in the previous video. However, the proof for when U is an open set is exactly the same proof. We never really need to use the map was globally defined. The proof when U is measurable is a little bit more technical. There are things to say, but actually for the implication for non-embedding, we don't really need this generality. We will really need use when the case when U is equal to G. So let me write some these notes. So first, for U open, it's the same proof we presented with U equal to G. And actually, for the non-existence of biLipschitz embedding, we only need U equal to G. Okay. But I still wanted to state a slightly stronger result, just for your knowledge. Okay, so from this theorem, when U is equal to G, let's prove the non-embeddability result. So proof of sense non-embeddability. Okay, by contradiction, let's assume one biLipschitz embedding exists. So by contradiction, there exists a map F from some set U of positive measure into Rn biLipschitz embedding. Let's denote by L the constant in the biLipschitz embedding, in the biLipschitz embedding condition. Now, so with U of positive measure, now, since it has positive measure, then we can take some points called P0 in U, a density point. So we know that almost every point is a density 1. And then what we do, we consider the dilated map. So F composed L P0, and then left translated by F P0 minus 1, we dilate delta epsilon, delta 1 over epsilon. Okay. Now this sequence may not converge. Okay. So as epsilon goes to 0, but what we have is that all these maps are L biLipschitz embedding for all epsilon. Now by Ascoli-Arzelà law, up to choosing some subsequence of epsilon going to 0, we have some limit. So we can choose some map, let's call it F tilde, which is the limit, let's say, of J going to infinity for some subsequence for some epsilon J converging to 0. So there exists some subsequence for which this limit exists, is a limit uniformly on compact sets. And what we have is that F tilde now is a map because P0 was a density point, then F tilde is defined on all of G. Because from G to same target was Rn, and is still an L biLipschitz embedding. Okay, therefore now it's a global map. We can use Pansu's version of Rademacher theorem. Okay, so by Pansu Rademacher, there exists a point P in G such that the intrinsic differential at P of F exists. So dPF now is really the limit, really for epsilon going to 0, of the same dilations. Or maybe I should not, let's call it F tilde. We are applying to F tilde. Compose L F tilde P, compose F tilde, compose LP, compose delta 1. Again, these maps here, they are all L by Lipschitz. L by Lipschitz. And therefore, dPF tilde is still L by Lipschitz embedding. From G to Rn. Being an L by Lipschitz embedding, in particular, the map has to be injective. Okay, so we get that the intrinsic differential, it's injective. But now remember that differentiability not only tells us that this limit exists, but it also a group homomorphism. So also, this was true for almost every P and G, D, P, F tilde going from G to Rn. Here with Rn we have the additive structure, is a group homomorphism. Being a group homomorphism then has to send the commutator subgroup inside the commutator subgroup of the image, of the target. But now, this commutator subgroup of the target, this is 0 because Rn with sum is abelian. Instead, assuming that G was a non-abelian group, then this commutator is not 0. So, since G was assumed to be not abelian, which therefore we have that dP F tilde is not injective. So we prove that there are intrinsic differentials that are at the same time injective and non-injective, and therefore we get a contradiction, which concludes the proof of Sem's non-differentiation theorem. Okay, let's take this as a corollary. There exist Alfors regular metric spaces that cannot be even locally biLipschitz embedded into the Euclidean space Rn. For example, any non-abelian Carnot group, and a very specific example is the subRiemannian Heisenberg group. Okay. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.